Yeah, we can hear
Yeah,
you.
we can hear.
Okay,
Yeah.
thank you so much. Thank you for confirming that. I want to welcome you to my lecture today. Of course, the reason why we are actually holding lecture remotely today is due to the winter storm alert that we got. So, but I can assure you, the way I'm actually going to conduct today's lecture will be we be the same as the way we used to do it. So now let's get started. Uh, you know, I'm actually going to go over this material with you today that I call principal component analysis. And on Friday, I'm actually going to walk you through midterm one practice questions. So the Friday's lecture will be dedicated to midterm one practice questions, and I'm also going to tell you some other you know stuff that you actually expect in the exam. But let me first welcome you to this lecture. We call that principal component analysis. Okay, so in the outline, I'm going to walk you through fundamental principle of a principal component analysis. Then we're going to go over application as well. And in the course of the lecture, if there's anyone want to ask question, of course, you are free to do so. Okay, so let's start with the principal component analysis. So I'm going to say this. You know, uh, there's a principal component analysis is actually an intervention. It means there have been problem. And what kind of problem are we talking about? We got problem of multicollinearity. I remember in one of my lectures, I told you multiple linear regression as assumptions. And one of the assumptions is multicollinearity. Actually, what multicollinearity talk about is, when the explanatory variables correlate. We don't want a situation whereby the explanatory variables will correlate. That is, we don't want them to have relationship. Of course, when they have relationship, what do we do? When they have relationship, there's basically going to be multicollinearity issue. The multicollinearity problem could be moderate, could be severe. Okay, a situation where it is moderate, of course, maybe we don't need to be worried so much, even though the regression parameter, the estimate of regression parameter, is still going to be unbiased. But the only thing is just like they are no longer going to be consistent. They are no longer going to be consistent because of the fact that the variance has been inflated. If I want to, when I have an estimate of a regression parameter, we can figure out the variance, right? If I'm talking about beta 1, I can talk about the variance of beta 1. So if I have a model y equal beta naught plus beta 1 x1 plus beta 2 x2, and so on like that. Okay. Now don't forget, when I got the estimate of beta naught, we can get the variance of beta naught. When I got the estimate of beta 1, we can also get the variance of beta 1. So now when multicollinearity exists and it is not severe, let's say it's moderate, okay, the regression parameter, we're still going to have situation where the expected value of this guy is still going to be this guy. Expected value of beta 1 cap is still going to be beta 1. Expected value of beta 2 cap is still going to be beta 2. So this 3 scenario is trying to tell the world, even though multicollinearity exists, okay, but maybe it is not severe, okay, the unbiasedness property is still going to hold. Okay, the unbiasedness property is still going to hold. Okay, now but except that the variance associated with the parameters is no longer going to be consistent in the sense that the variance will be inflated. And why do I need variance of age? Why do I need variance? Of course, without variance, there's no way I will be able to get a standard error. And if I want to do statistical inference, right? I need a standard error to do inference. What do I mean by inference? Maybe I want to construct a confidence interval on beta naught or beta one, or I want to conduct hypothesis testing, whichever way. If I want to construct confidence interval or I want to construct an hypothesis testing, of course, I need a standard error. And there's no way I'm going to get standard error if I'm not able to get the variance. So when the variance is inflated, the standard error will be inflated. Of course, that may lead us taking a wrong decision at the end of the day. Okay, but when it is severe, of course, you will not even be able to estimate your regression parameter. That is when it is severe. And remember, I walk you through how to fix the problem of multicollinearity the other time. By using what I call the standardization. I walk you through standardization. Okay, standardization. But you know what? The use of standardization we ensure that we don't discard any variable from the model. Okay, that is one approach to fix multicollinearity. Now, what I want to walk you through today is another approach to fix multicollinearity, which I call the principal component analysis. So, which means another alternative intervention to fix multicollinearity problem is using principal component analysis. Now, what principal component analysis we do is, when I have so many explanatory variables in my model, there is tendency that they may correlate. And when they correlate, that leads to multicollinearity issue. So in order for us to solve the problem of multicollinearity, we can actually use a feature elimination. So one of the property of principal component analysis. So if I want to solve the problem, if I don't want multicollinearity anymore, I can actually reduce the dimensionality of my, of the situation, or I can do feature extraction. The feature extraction is just like, okay, instead of working with so many variables, why can't I just select those that are reasonable? So we have, when we're talking about dimensionality reduction types, we have a feature elimination, we have a feature extraction. Of course, when you do feature elimination, it means, well, how can we eliminate some explanatory variables that are not that important? Because when you don't eliminate them, they will be causing problem. And how do I extract the important one? That is feature extraction. Okay, so I'm going to walk you through an example right now. Okay, the example that I have right now, we in the GDP example, like instead of considering, maybe we're looking at some, determinants of economic performance, and we got a lot of variables. Okay, we might decide to drop all variables except maybe the three important ones that we think, okay, we best predict the United States of GDP. When you are doing that, you are actually eliminating some features that you believe that are not important. How do you know that? Maybe because from the literature review you have reviewed, from the article you have reviewed, you realize that some variables are not that important. Why can't we remove them? Because if you don't remove them, of course, there could be a problem of multicollinearity. And of course, the advantage of feature elimination method will include simplicity. Simplicity in the sense that you don't have so many variables anymore. And if you don't have so many variables anymore, of course, it means your interpretation will make sense. Because let me tell you the other time, I told you the other time, when we're doing research, we need to, decide on, do we want to predict or do we want to explain? If you want to explain, you don't need so many variables. I'm going to say that again. If you want to explain, if you are pursuing an explanatory goal or you are pursuing a causal goal, you don't need so many variables. Because if you consider so many variables in your model, your interpretation will be lost. I'm going to say that again. When you got so many variables in your model, interpretation will be lost. And that is the reason why you are trying to extract those features, those variables that are actually important. And you are eliminating those the irrelevant ones. And we are actually doing that because uh, for you to be able to maintain the interpretability of your variables. What I told you, when you got a lot of variables and you are pursuing an explanatory goal, okay, when you got a lot of variables, then your interpretation will be lost. Can you say confirm again if you are still hearing me? Is everyone still hearing me?
Yeah.
Okay, thank you so much. Thank you for confirming that. Now, what is now disadvantage? We know the advantages of feature selection is just like, okay, that will enable me to have few variables in my model. And when I got few variables in my model, my interpretation is going to be great. Okay. But what will be the disadvantage? Okay. It means, the one that you drop, okay, which means you gain no information from those variables you have dropped, because dropping them, you've lost information about them forever. Okay. And that was why I say if we use last year GDP, the proportion of the population in the manufacturing jobs by the most recent American Community Survey members and the employment rate to predict the year GDP, we're missing out on whatever the job variable could contribute to our model. That's what we're missing out. And by eliminating features, we also entirely eliminated any benefits those drop variables will bring. Let me tell you this. When you are pursuing a predictive goal, you need a lot of variables to do that. Because in a predictive goal, you are not interested in explanatory. So you don't need interpretation. You don't need what the effect of what variable is on another variable. But what you basically want to figure out is you actually want to have the best prediction. And that is the reason why, the machine learning expert is basically going to consider all of that. It's not like they're going to drop any. But there's a disadvantage for that. Disadvantage is, okay, when you use all of that, you cannot interpret regression coefficient anymore. But it will serve your purpose of your predictive goal. Okay, now, for the feature extraction, I said for feature extraction where you extract, so that doesn't run into this problem. Say we have 10 independent variables, that is 10 explanatory variables. And in feature extraction, we create 10 new independent variables. Okay, we are each new independent variable. Okay, now let me now tell you this. The principal component analysis is a feature extraction technique. I'm going to say that again. Principal component analysis is a feature extraction technique. Now, feature extraction technique in such a way that if I have 10 variables, that they are correlating, right? It's a multicollinearity problem. They are correlating. What I'm going to do is the principal component analysis will enable us to produce a brand new 10 variables, brand new 10 variables. And each of the brand new variable will be a linear combination. This is what I'm going to say. For instance, if I have x1, x2, x3, dot, until I get to x10. Initially, I got 10 variables, right? And they correlate. Okay. Now, what we're going to do in feature extraction, which is a technique of principal component, is that I'm actually going to produce a Z1, a Z2, up to Z10. And the Z1 is going to be a combination of the old variables. The Z2 is going to be combination of the old variables up to Z10 is also going to be a linear combination of all the old variables. That's exactly what we mean by feature extraction. And we said, however, we create these new independent variables, okay, in a specific way, and other these new variables by how they they predict our dependent variable. So which means what I'm trying to talk about now, irrespective of the numbers of independent variables that you have, if they correlate, using the idea of principal component analysis, we're going to create new set of variables. The new set of variable, each of the new variable will still be a linear combination of the old one. And you know what that means? It means in a way, we don't lose information entirely about the old one. But when you take a look at the elimination, you are just dropping. Okay, if maybe you have 10, you drop 5, then you've lost information about the 5 that you drop forever. Any benefit of that, that may contribute to the response, you've already lost that forever. That is what we mean by feature elimination. But in feature extraction, which is the basic principle of principal component analysis, we're actually going to replace if we have 20 variables, we're still going to have 20 new variables, where each of the new variable will still be a linear combination of the old variables. Now, when should I use PCA? When should I use principal component analysis? Okay. Number one, do you want to reduce the numbers of variables? Okay, but you are not able to identify variables to completely remove from your consideration. At times you want to you don't want to do you don't just want to do feature elimination because maybe you have a strong statistical backing or theoretical backing that variable should be included, even though the variable is causing a problem. And you don't want to just eliminate, because when you eliminate that, you're actually going to lose information about the variables that you eliminate forever. And what you now want to do is, okay, you can decide to think about using the principal component analysis. So the principal component analysis will only help you to create new variables, except that each new variable will still be a linear combination of the old variables, which means in a way, you are able to actually retain information about the old variables in your model. Okay. So number two is, do you want to ensure your variables are independent of one another? I can actually tell you the principal component analysis can guarantee guarantee uncorrelated relationship. What I mean is a technique that has proven to convert correlated variables into uncorrelated ones. Then are you comfortable making your independent variables less interpretable? Okay. And if your answer is yes to all these 3 questions, then the principal component will actually be a good to use. But if you answer no to question 3, you should not use PCA. When you take a look at question 3, if the answer is no, are you comfortable making your independent variable less interpretable? If the answer to that question is no, then you shouldn't use PCA. Okay, now how does PCA work? I think I've just justified, using the PCA, right? So how does it actually work? Okay, now If y variable exists, which is the response, and is part of your data, then we're going to separate data into y and x. You know, the x that I mean here is explanatory variables, which may be 10 of them, 5 of them, and so on like that. So we're actually going to be focusing, using the principal component analysis. We're not interested in the response. We're not interested in the response, but we're actually going to focus on design matrix X. You know why we're focusing on X? Because multicollinearity that exists among the explanatory variables. That is why the focus is going to be on X. So what we're going to do, we're going to take the matrix of independent variable X, and for each column, we subtract the mean of that column from each entity. It's more or less like we are doing centering. You remember the other time when we talk about, centering, okay? You have a random variable x1, you remove the mean of that. You have a random variable x2, you remove the mean of that. That's exactly what I mean. And when you do that, that ensures that each column has a mean of 0. Okay? Each column is basically going to have a mean of 0, because you know why? The sum of the deviation, sum of xi minus x bar is equal to 0. Sum of the deviation equal to 0. Okay? Now, that is step number 2. In step number 3, you decide on whether or not to standardize. What do I mean by standardization? You remember? The standardization is basically going to be x minus si, like zi is going to be minus the mu I divided by standard deviation. You remember is z score, right? So we need to decide on whether or not to standardize. Okay. So given the column of x with a feature with a high variance, more important than features with a lower variance. Okay. If a situation where you look at your data and you realize that, feature with the high variance are more important than feature with the lower variance. Okay. Then in that situation, you may basically want to say you standardize. But I'm actually going to tell you, in general, standardize. Okay. You remember where we were facing multicollinearity the other time in one of my classes, that we use the idea of standardization. Okay. Now we're also going to use the idea of standardization here. Now we got a design matrix X, and we standardize. And when we standardize, we are actually going to have a matrix Z, because don't forget, each of the explanatory variable will be standardized by subtracting the mean of that particular variable from that variable divided by the corresponding standard deviation. You get that, right? Now, the next thing we're going to do is to find the transpose of Z. When we find the transpose of Z, which is basically going to be this guy, then we're going to multiply by the original Z, okay, which we're actually going to call the resulting matrix is the covariance matrix of Z. Covariance matrix of Z. And after that, the moment you have the matrix of, you have that, then we need the eigenvectors and the eigenvalues of that. I'm going to say that again. We need the eigenvectors and the eigenvalue for that. Okay. So now, when you take a look at what I have now, the mathematical, for instance, if you take a look at this guy here, if I want to go mathematical, you know what I'm going to do? It's going to be the absolute value, the determinant. Okay. So the matrix minus lambda high equal to 0. Don't forget, this guy is this guy here. Okay. If it is 2 by 2, the identity matrix is going to be 1 0 0 1. If it is 3 by 3, identity matrix is going to be 1 0 0 0 1 0 0 0 1. Take a look at that. Okay, and the lambda here is basically going to represent the variance. Because at the end of the day, when you get the agent values, okay, your agent values is basically going to be lambda 1, lambda 2 to lambda p, which is going to be arranged from the largest to the smallest. The largest is going to be the largest contribution, which is the largest variation, in that very order. And in the end, we're actually going to calculate that, which is now, I'm going to show you how we're going to do this in R. But I still need everyone to confirm again if you are still hearing me clearly. Is everyone still hearing me clearly?
Yes.
Yeah.
Yes.
Okay. Okay. Thank you so much. Thank you for confirming that. Now, I want to show you a result, but my TA is basically going to walk you through how to go about this in the lab. I'm also going to supply you're going to see a code on how to do that. Now, I'm actually want to use a data set that we call rate my professor data. In the rate my professor data, we consider 5 explanatory variables. Okay, if you take a look at what I have here, we actually we got quality, helpfulness, clarity, easiness, and rate of interest. These are the kind of variables that we actually we collect data. Students rated their professors over this using this over this variable. Okay, the range is from 1 to 5. 1 is worst, 5 is the best. Okay, and we realize that these variables correlate. Okay, they correlate. There's a problem of multicollinearity. Okay, and when there's a problem of multicollinearity, what you're actually seeing here, this is like x1, x2, x3, x4, x5, all the predators here, all the explanatory variables. Okay, they actually have relationship. They shouldn't. Okay, and because of that, okay, we actually want to use principal component analysis to fix the problem of multicollinearity. Okay, now in fixing the problem, what are we going to do in fixing the problem? We actually want to use the principal component analysis, and of course, the principal component analysis before first start from centering. What is the centering? I'm going to get a mean of the quality. You get a mean of helpfulness. You get a mean of all the variables, and you're going to create a new variable that's basically going to be x1 minus x bar 1. Okay, for all the data in quality. I'm also going to do it for all the data in helpfulness. Okay, that is the centering. I'm going to do that all the way to the last data. Okay, to the last variable in the data. That is centering. You centered. And after that, you standardize, which means on this guy, I'm actually want to get a Z1. The Z1 is basically going to be x1 minus x bar 1 divided by the standard deviation of that. I'm also going to do the same for Z2 until I get to Z5. Okay, and when I got that very Z now is going to be a matrix. I'm actually going to get a Z transpose. Then I'm going to multiply by Z. Okay, when I do that, then I need to get my lambda. And the only way to get the lambda that I call the agent values now, okay, because I need to get my agent values before I get my agent vector. Okay, my agent values now, if I want to get that, if I want to go by mathematical way, I'm actually just going to be this guy minus lambda high, determinant of that equal to 0. Okay, now when you take a look at the lambda here, this is basically going to be 5 by 5 matrix because I got 5 variables, which means I'm going to have lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. And let me tell you, R will automatically compute that for you. And take a look at this. What do you see? That is your lambda 1. Your lambda 1 is going to be the largest, 2.39. Lambda 2 is 0.39. Lambda 3 is 0.22. Lambda 4 is 0.06 and lambda 5 is 0.00. Take a look at that. So the largest, so what is the implication of what we're talking, of this, when lambda value is that, okay, and you basically want to figure out what is the proportion of that particular lambda. For instance, do you know how they got is 0.78, right? The 0.78 is just going to be 2.39 divided by the totality. Okay, it's like you want to get you actually lambda 1 divided by lambda 1 plus lambda 2 until you get to lambda 5. Okay, that proportion is 0.78. You're going to do the same thing. Okay, for this guy, it's going to be 0.39 divided by the totality. Then you're going to get a 0.13. So now with that, you're actually going to get the proportion of the variance. Oh my God, the proportion of the variance is actually telling you the relevance of the the principal component variables that you just saw, the variables you created. Take a look at that. Now, if I now want to get that cumulatively, of course, when the first component is 0.78, of course, I'm not going to have a 0.78. Okay, now, if I want to use a combination of the first and the second principal component, that's actually account for 91%. Okay, if I want to combine the first three principal components, that will account for 98%. If I want to account for, four principal components, that will account for 100%, but we got a threshold in statistics. The threshold is at least 80%. When the cumulative is at least 80%, we are fine. So which means we're only going to settle for the first and the second principal component, because cumulatively the two of them actually explain 91%. And don't forget, the threshold is 80%. So which means we are not going to use all the principal component that we have created. Don't forget, initially we got 5 variables. They actually correlate. Don't forget that they correlate. And when they correlate, we derive a new 5 principal components, 1 to 5. Don't forget, each of the principal components is a linear combination of the old one, of the old variables, but in the end, we're not going to use all the 5 new principal components. We're only going to use 2. Why are we using 2? Because the combination of the 2 exceed the threshold of 80%. The combination of the 2 actually give 91%. Okay, now it means I'm going to be focusing on this particular 2. Now, the next thing is I need the agent vector. Okay, I need the agent vectors, okay, that correspond to each agent value. Okay, to each agent value. If you take a look at this guy now, that is the first principal component. The first principal component has all the variables. Look at that, of the old variable. The second principal component also has all the old variables. But based on what I'm trying to show you now, the fact that looking at the cumulative proportion, we're only going to focus on the first 2 principal component, because of the fact that the first 2 principal component display 91% of the variation, and because of that, we're not interested in this guy. If we're not interested in the principal component number 3, number 4, number 5, we're not also interested in their corresponding agent vector. Is there anyone who need clarification on what I just explained now? Is there anyone?
Where do the eigenvectors come from?
Okay, that's a very good question. Somebody said, where does the agent vectors come from? How do we automatically compute? Okay, let me show you how do we automatically. Now, can you take a look at this? How we're going to do that now? In the rate my professor data set, in the data frame is from column 1 to column 12. but I'm only focusing on 5 variables which occupy column 8, column 9, column 10, column 11, column 12. Okay? What is the next thing if I have a principal if I have the next step is to standardize. You remember? How do we standardize? In a principal component in R is this guy here. That's what I'm doing. PRCOMP scales. Okay? And when I do that, when you write that, take a look at it. Arrow will automatically generate that for you. Do you know what Arrow is generating for you now? That is your eigenvalues. So which means it's lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. And Arrow will also generate the eigenvector. We also generate this guy. Okay? So this PC1, PC2, PC3, PC4, PC5, and this guy here will be automatically generated the moment you write that code. Does that make sense to you now? Does that make sense to the person that has the question?
Yeah, that makes more sense.
Okay, now take a look at this. This is, if I want to go by what I just explained now, okay, I need to fall first. These are lambdas. We call the eigenvalues. This is lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, and all this lambda actually is basically going to give you the amount of variation, each principal component, explain. Lambda 1 will always be greater than lambda 2. Lambda 2 will be, it's basically going to be lambda 1 greater than lambda 2, greater than lambda 3, greater than lambda 4, greater than lambda 5. Now, the moment you have this, the next thing we're basically going to do is, what is the percentage contribution of each lambda? If I want to figure that out, if I want to know the percentage contribution of that, it's basically going to be 1.89212 divided by the totality. So I'm going to do the same thing for this guy, for this guy, for this guy, for this guy. When I do that, the next thing is to do the cumulative that I'm doing here. Let's say this is what I got first. Then the next thing is to get the proportion of the variance that I talk about. Then the next thing is to get the cumulative. Why am I getting the cumulative? The cumulative is just to be able to, for us to know how many principal components do we need to combine, because we're not going to use all the principal components. That is the idea. Even don't forget, each principal component also contain the whole variables. Okay, the information is not lost. Now we got a threshold, like I said, the threshold of 80%. And when you look at the combination of the first and the second principal component, it's actually give us 91%. And that is the reason why our focus we actually going to be on the only 2 principal components. So that is what the arrow is giving you here. So this is the first principal component. It has all the old variables. The second principal component, the third principal, the fourth one, and the fifth. But based on the threshold that I just talked about now, we're not basically going to use all of that. We're only going to use the first 2. We're only going to use the first 2 provided the cumulative is actually 80%. Okay? Does that make sense? Now, after doing that, like I told you, if you want to do that in R, the moment you first declare your variable, then you standardize that and you write a PR or, principal components, scale of that is going to give you the first output you're actually going to have will be eigenvalues. Okay. The first one you're going to have will be eigenvalues. And then you're going to have both eigenvalues and this guy here. Okay. And the other principal components. So these guys here, they are more or less what we call eigenvectors. Eigenvectors. Okay. Now, the moment you have that, if you now need information about the percentage of variation, the contribution I talked about the other time, you just need to come to the summary. Just say summary Z. Where is your Z? Okay. Your Z is actually this guy here. So when you do the summary for Z, automatically, you're basically going to have that. Arrow has automatically, it has done that for you. Now, I got 5 principal components, and I want to look at, this is their agent values. Okay, the agent values. Then what is the proportion now? The data has already computed the proportion for you. Now, then it has computed the cumulative. Oh my God. Oh my God. The combination of this guy, those two actually give it is 7.6%. So what was the threshold? The threshold is 80%. So which means in this principal component, I'm only going to use the principal component 1 and the principal component 2. Look at that. Look at that. So I'm using the principal component 1 and 2. It means I'm actually going to go back. It means I'm going to be focusing on this guy and on this guy. And don't forget, in each of the principal components analysis, in each of the principal components, you still have the hold variables. You still have the hold variables. Okay? You still have the old variables, and don't forget, you are no longer using this guy here. You're not using this guy anymore, because the combination of the two principal components, okay, is enough for you. Okay, it's actually reached the threshold. Is there any question at this time? Is there any question? Is there any question? Now, if you really understand the principle, the way the principal component analysis work now, if you really understand the way I've explained this, I need you to say yes, or you comment yes, if you really understand what I've just explained. Okay, 1%. And if you don't understand, oh, okay, I got a good number of good job, which means everybody understand. Okay, I'm actually going to have a recap again on what I've explained today. The purpose of today's class is just to walk you through another way of fixing multicollinearity problem. You remember in class, I walk you through one way of doing that, which okay, somebody chat with me now. Somebody say, how would the model look like? Okay, if you want to write a model out now, okay, you're actually going to write PC1 equal negative 0.5176 quality. I'm not going to write quality in full. I can just say Q, okay, minus 0.5090-ish. That is F-ness, right? Minus 0.5053C, okay, minus 0.3537E. So that is easiness, right? The last one, minus 0.3042R. So that is the principal component 1. I'm also going to write the 2. For the 2, the principal, of course, you know what I'm going to do. Does that mean now the person that has the question, do you now understand how? Okay, thank you too. So that is how you basically going to write a model. So which means the 2 principal components that you are actually using, the PC1 and the PC2, they are not going to be correlated. They're not going to correlate at all. In fact, all the principal component here, the PC1 up to PC5, they will never correlate. Okay, they will never correlate. Okay, so the advantage of using the principal component analysis is just like the principal component analysis is not a feature elimination. You know why? Why it is not a feature elimination? Because you still have the old variable in each of the principal components. You still have the old variable. That's why it's a very good one. So it's not a feature elimination at all. Okay, but it's more or less like a feature selection. I think you basically want to see what I mentioned the other time. So it's something that is a technique that we call feature extraction. And the only thing is extracting here is only extracting out of the new variables. It's not as if it's extracting from the old one. It's extracting from the new variable. The old ones they are still intact. So it doesn't fall under feature elimination. In feature elimination, that is where you're going to say, okay, I'm actually going to drop some variables that are not relevant, maybe based on the fact that you've reviewed literature and you are guided theoretically to do so. That is feature elimination. But for feature extraction, that is where, the principal component analysis is basically going to work, because it's only going to extract those new variables that you create. You're going to extract out of those new variables why you are still retaining the old ones. And that's exactly what I've demonstrated to you now. So today, I think I've demonstrated how you can do that manually, and how you can actually use R. So how you can do that, when you look at the approach, we did not consider response variable at all. When you're dealing with the principal component analysis, you don't talk about response variable at all. We only focus on the Z. We only focus on X, the explanatory variable. And of course, this is the code in R. How are you going to do that in R? You focus on X. There's nothing like Y. There's nothing like response. Okay? You extract your variable X. You scale that. You get your agent values, which are the lambda, which are the variances that are arranged in descending order. Then you're actually going to see the agent values. You're going to give you 5 principal components, which is a combination of a linear combination of the old ones. Then you can do the summary Z, and that will give you the proportion of variance. We actually call this importance of components. It is not all components that you're basically going to use. At the end of the day, we got a threshold. Okay, and of course, the combination of the principal component 1 and 2 actually explain 87.6%, and we got a threshold of 80%, and that is the reason why we're actually going to focus on PC1, PC2. Oh my God, this is where I'm actually going to stop today. If you really understand the principal component analysis that I've presented today, I need you to say yes, or you comment yes. Okay, good job. Okay, now I want to appreciate every one of you who have attended my lecture today. Let me tell you what we're going to do on Friday. What we're going to do on Friday is basically going through midterm 1 practice questions. On Friday, I'm going to tell you from the area of coverage for the midterm 1, and I'm going to go over the midterm 1 practice question that I've already published, and I'm also going to give you some information about the midterm 1. That will be the focus on Friday. So I'm actually going to see you in person on Friday, but you know what? Make sure you stay safe. When you're going around today, the snowstorm alert is it's in effect. So you got to make sure you are very, very extra careful when you're walking around. Okay, until Friday that I'm actually going to see you in person. Make sure you stay safe. Have a very wonderful day. Bye for now, everyone.
Thank you.
Thank you too. Thank you,
So
everyone.
bye.
Yeah, bye.
Thank you.
You're welcome.
I have a question about like the PC1, PC2 stuff, like the model.
Okay, go ahead.
I'm not confused. Like, when should I use PC1? When should I use PC2? Like, how these are related to each other?
Oh, even though you have 5 principal components,
yes,
the idea of the feature extraction is that we're not going to use all the 5 principal components. So we're going to look at the first, even if the first one, let's say, I'm going to share something now.
Yeah.
Let's say the first one, if the first one is already 80, okay? If the first one is already 80, it means you're only going to use, give me 1 second, I think it's sharing now. Yeah, go ahead.
I mean, yes, but in this case, since first one is only 78%, we use the first 2. Like, how does these two affect each other when we're using the model?
They are not going to affect each other because the two of them will be orthogonal. They are independent on their own.
Yeah.
And you know, that is the assumptions in regression, that the explanatory variable should be independent. So
Yeah.
the relationship they have with each other is that they shouldn't have any relationship at all. So which the principal component, which we've already achieved with the principal component. I don't know why this is not sharing. Can you give me 1 second?
Yes.
I basically want to know. Oh, okay. I think it should share now. Give me 1 second. It should share now. It should share now. Okay, can you see that, right? Has it shared already, right? Okay, now you were talking about, can you hear me?
Yeah, I can see you.
Okay, you're talking about this guy here, right?
Yeah.
Now, what I'm trying to tell you, all these principal components that you just created,
yes.
they are independent. They are no longer dependent, which means they satisfy assumptions of
Yeah.
using them. Now, if you look at the first, the principal component one alone only account for 78%.
Yeah.
But when I use a combination of the two, what do you say?
It's 91. Yeah, that's my question. Like, so we are using the combination of one of two. How we write a model that's
Yeah, okay, if you want to write the model now,
yes.
you're only going to write this model. Like, this is what I said. Like, for instance, the principal component 1 minus 0.535 quality minus 0.529 F-ness minus 0.537 clarity minus 0.336 easiness minus 0.181. So this is a first principal component, which means I'm using that. That's a model 1.
Yeah.
Model 2, principal component 2 will be minus 0.155 Q.
Sorry.
I'm also going to go that way
Yeah.
too. Does that make sense now?
Yeah, that makes sense. Like, I know that, but since we are using both models, how we use the results from these two models instead of using this one? Like, I mean, when I use just one, for example, just the PC1, I can just plug the numbers in and I get a estimate result. But now we have two models. How these two results affect each other?
Oh, that we actually going to use. Okay, in my next lecture, I think I understand what you mean now.
Yeah.
So what we are actually trying to tell you is, in the principal component 1, okay, we actually we see how what we call further analysis that I'm going to present next. We are still on principal component analysis. I understand what you mean. Like, okay, now we have arrived at 2 principal components. Then how do we now use the 2? Is that your question, right?
Yeah, like.
Oh, we're gonna do that. We're gonna do that next.
Oh,
That's
okay.
what we're gonna do next. Yeah.
I see. Thank you.
You're welcome.
Yeah. Have a good night.
Good night. Yeah. Okay. So for now.
Yeah.